We've seen that water in the unsaturated zone exists under tension. It's at a pressure that's lower than atmospheric pressure. But just how low is it? How would we measure such a thing? And how does it vary as a function of water content and the type of material that it's in? These are the things that we are going to explore in this video, or at least begin to explore. And we're going to start off by depicting a very simple apparatus that will enable us to tell the pressure of the water in a sample in relation to how much water is in there. So start with some known cylinder that's open at the top. It's a known volume, and we've filled it with a soil sample. So some particular grain size distribution. And at the bottom, instead of there being a solid bottom, there's a ceramic plate. And the idea with this ceramic plate is that the pores in this plate are too small for the soil particles to go through, but liquid water can exist continuously on either side of the plate. So, and it can flow back and forth through the plate. So this ceramic plate then goes down into some sort of a funnel, and then there's basically a tube that's open at the atmosphere over here. This tube is called a manometer tube. And it's filled with water. And it's in continuous liquid contact with the water that's in the soil. And so this is all just water here. There's water here, there's water here, there's water here, there's water here. And then we're going to start with a totally saturated sample. So this sample here is initially saturated. Okay, the beauty of this particular apparatus is the following. We can do two things. We can lower this tube so that water flows out. And what that'll do is it will also cause a decline in water content in the sample. But as we lower the tube, we're going to be able to relate the height difference here to the height of water in the sample. And you can imagine that you could lower this tube quite a ways and it might still have water in it. And that's because the water is being pulled by the water here in the soil that's under tension, and it's not going to flow out. So, and the height that it drops is going to tell us something about the decline in pressure of the water in the sample. So it's a very simple setup, but it gets these two key measurements: the pressure of water in the sample, and because we can measure how much water comes out, and we know the starting volume, we know the amount of water that remains here in suspension. So this is the experiment. It's the exact same thing. There's a ceramic plate. We've got our soil sample here. But the idea now is that we're able to lower this tube such that this difference in height is telling us what the pressure component of head is inside of the sample. So there's continuous liquid water here, and it's out to here. And the other key thing is that as this water comes out, we're measuring it, and this is supposed to just show you like there's a measuring cup or something. And so we're able to do this experiment. And the experiment goes in steps. So this is the experiment. We want to lower the tube incrementally, so maybe a centimeter at a time. And we want to measure the water that comes out, so the volume. And we want to calculate the volumetric water content that remains here in the sample as we start to desaturate the sample. So there's still water in here, but there's air that's entering in here as we're draining this. And we want to also be calculating and relating this to the water potential here. So as we're doing this experiment, we're collecting the data, and on this axis here, we will have the water content theta going, let's say, from 0 up to 0.4. We'll have this be equal to the porosity of our sample. And on this axis here, we'll have the axis be the negative pressure head. Or you could also think of this as the tension of the sample. So it's negative psi, and the units are going to be in meters. And we'll go out here to 1. 1.0, 0.75, 0.5, 0.25. And so as this experiment progresses, we start here. We're allowing the pressure to drop, but at first no water comes out. And so we have kind of a constant amount of water, but then we start to see it plummeting. And so as we keep lowering the tube down, we do start to eventually desaturate here. And we see that some curve emerges, and we could connect all these points here and establish this relationship, which is called the water characteristic curve. For a given sample with a particular grain size distribution, the water characteristic curve relates the volumetric water content of the sample to the pressure head of the sample, particularly as you're starting to desaturate the sample and you're getting into these negative pressure heads.